In this next video, we're going to take a closer look at some of the properties of unit cells, and in particular, we're going to be looking at cubic unit cells. What we would like to understand is how is the radius of the atoms that we're stacking related to the size of the unit cell, and realize that that's going to be different depending on the type of unit cell that we have. So we're going to be mainly focusing on simple cubic unit cell, body-centered cubic unit cell, and face-centered cubic unit cell. So an interesting question is how many equivalent atoms are there in different types of unit cells? So let's start with the simplest unit cell, which is that simple cubic unit cell. And we said that for a simple cubic unit cell, we have one atom centered at every corner of a cube. And then to build up the lattice, we're going to stack all of those cubes together so we end up with a three-dimensional crystal. So when we think about that, we will see that one atom that is in a simple cubic unit cell, when we stack all of those guys together to build the crystal, we will see that that corner atom will be shared by 8 unit cells. So that's kind of, it takes a little bit to get around that. Models really, to get your mind around that, models really help, but we don't have the opportunity to play with models in an online class. So we know that for every atom that's at a corner, it's going to contribute 1/8 of an atom to a single unit cell. And in a single unit cell, there is 1, 2, 3, 4, 5, 6, 7, and you can't see number 8, 8 corners. So an atom that is placed at the corner of a unit cell, that's going to contribute 1/8 of an atom. There are 8 corners, so in total, in the simple cubic unit cell, we have 1 atom. So let's do the same thing now for the body-centered cubic unit cell. So in the body-centered cubic unit cell, you have an atom centered at every corner, and then you have one atom right in the middle of the unit cell. So it looks like this, right? Okay. So we know that an atom that is at the corner, that is going to be shared by 8 other unit cells, and that there are 8 corner atoms. So we're going to get one atom, 1/8 of an atom for every corner, multiplied by 8 corners for the corner ones. That's going to tell us how many atoms we get just for the corners. So now we need to think about that atom in the middle there, right? Now, can this atom in the middle here be shared with any other unit cells when we start stacking these unit cells? And the answer is no. It's completely contained within a single unit cell, and when we stack these guys together, it's not going to be shared with any other unit cells. So you get an additional atom in the body-centered cubic unit cell for the one that is in the middle of the unit cell. We call that the body-centered atom. So the body-centered cubic unit cell, you get 2 atoms per unit cell. So let's keep a tally. Simple cubic, you get 1 atom. Body-centered cubic, you get 2 atoms per cell. Okay, so we've got another type of unit cell that we'd like to look at eventually, and that's going to be the face-centered cubic unit cell. So in the face-centered cubic unit cell, you got an atom at each corner. There are 8 corners, and each of those atoms contribute 1/8 of an atom. That is, they are shared with 8 other unit cells. So now we have to think about, what about these ones that are in the middle of every face, right? And an atom that is in the middle of a face is shared between 2 unit cells. Just when those 2 unit cells touch, then that atom at the centered in the middle of the face there will be shared with 2 unit cells. So how many faces do we have on a cube? We said that we've got 6 faces. And then you get half an atom for every face. So half an atom for every face, and you've got 6 faces. That's going to give me 3 atoms. So for the corner atoms, you get 1/8 of an atom per atom that's at a corner. and you've got 8 corners, that gives me 1 atom. And then you get half of an atom for an atom that's centered in the middle of a face, and you've got 6 faces, that gives me another 3 atoms. You add those together, you get 4 atoms per unit cell. So a simple cubic unit cell, you get 1 atom per cell. A body-centered cubic unit cell, you get 2 atoms per cell. And then a face-centered cubic unit cell, you get 4 atoms per cell. So it's not very surprising that the packing efficiency increases as we move from simple cubic, body-centered cubic, face-centered cubic. Okay, so we said that we wanted to relate the radius of our atom to the length of the unit cell, right? To the edge length of the unit cell. Okay, now the edge length in every case, as I pointed out, for a cubic unit cell, it's going to be the same for all of the edges are going to have the same length, right? It doesn't really matter what one we look at. So for simple cubic unit cell, we can see that the atoms touch along the edge of the unit cell. So going from here to here is 1 times the radius. And then going from the center position to the outer edge here, that's 2 times the radius. So the edge length of the unit cell is equal to 2 times the radius. So if you know the radius of your atom, you know the edge length of your unit cell, or vice versa. Okay, so that was kind of pretty easy. If I know the radius, if I know the edge length of my unit cell, I can calculate the volume of my unit cell just by simply cubing the edge length. So, and again, I can relate that back to the radius if I want to. Okay, so let's move on to the next example and see if we can do a similar analysis relating the edge length to the radius. So in the face-centered unit cell, the atoms touch along what's referred to as the face diagonal. So this is, the length of this diagonal can be calculated using the Pythagorean formula. So L squared plus L squared is equal to the face diagonal length squared, right? So 2L squared equals the face diagonal length squared. And then I can kind of take square roots and reorganize, and what I end up with is that the face diagonal, the length of the face diagonal is equal to root 2L. Okay, so you know that's not too hard to see that. How many radii of our atom go across that face diagonal? Well, we can count that up from a little model. The important thing to recognize is that in the face-centered cubic unit cell that the atoms touch along the face diagonal. There they are. And so we've got 1 radii to there. A second radii takes us to the very middle of the face. A third radii takes us to here. And the fourth radii takes us to the other corner. So another way of expressing the length of the face diagonal is to say that it is equal to 4 times the radius of our atom. And so there's our relationship. Root 2 times the length is equal to 4r for face-centered cubic. All right, that's how those guys are related. Again, if I want to, if I can solve for my edge length, I can always cube it and solve for the volume of my unit cell. All right, so we're only missing one now. We need to look at what it is for body-centered cubic unit cell. So the body-centered cubic unit cell is a little more complex. The atoms touch along what's referred to as the body diagonal. So if we go from the bottom front corner all the way up to the top back corner, that's where they touch, and that length through there is going to be 1r, 2r, 3r, 4r. So the body diagonal has length 4r when expressed in terms of the radius. Now, can we express the length of the body diagonal in terms of the edge length of the unit cell? So we can draw a right angle triangle where one edge is just the edge length, one edge is a face diagonal, and one edge is the body diagonal, and that will give us a right angle triangle. And then we apply Pythagoras again, so it's going to be L squared plus L root 2 squared is going to be equal to the body diagonal. Okay, so when I solve for my, I wrote that out over here already. So when I solve for the length of my body diagonal, it ends up being that the body diagonal has a length L root 3. So L root 3 is exactly the same length as 4R. So how are these guys all related? So for simple cubic, what we have is 2R equals L. For body-centered cubic, this is the one that we've just been looking at, L root 3 is equal to 4R. And for face-centered cubic, we have that L root 2 is equal to 4R. So you need to have that information at hand as you're working through problems based on this content. Okay, so let's kind of summarize it all. If you have an atom that's in the center of a cubic unit cell, that's going to contribute a whole atom. We commonly see this in our body-centered cubic unit cell. If you have an atom that is centered in the middle of a face, that will contribute half an atom to that unit cell. And we're going to see these types of atoms in a body-centered cubic, in a face-centered cubic unit cell. If you have an atom that is centered at the corner of a cubic unit cell, that's going to contribute an eighth of an atom. And we see these types of atoms in all of the 3 cubic unit cells that we've been looking at. So using this information here, the contributions of the different atom types to cubic unit cells, we can go ahead and calculate how many atoms there are in the 3 different types of unit cells that we're interested in. So you get 1 atom per simple cubic unit cell, 2 atoms for a body-centered cubic unit cell, and 4 atoms for a face-centered cubic unit cell. We went ahead and noting that cubic cells touch along the edge of the unit cell, that the atoms in cubic unit cells touch along the edge of the atom, that the edge of the unit cell, that the atoms in body-centered cubic unit cells touch along the body diagonal of the unit cell, and that atoms in the face-centered cubic cell touch along the face diagonal. We were able to establish relationships between R and L. And here they are here. For simple cubic, R is equal to L on 2. I actually tend to remember it like this. L is equal to 2R. For body-centered cubic unit cell, you can remember that root 3L is equal to 4R. But if you reorganize that, that is that R is equal to L root 3 on 4. And then for face-centered cubic unit cell, so root 2L equals 4R, which if you reorganize gives you R is equal to L root 2 on 4. So what have we got? Well, we know how many atoms are in each type of unit cell. We know the relationship between R and L for each unit cell. The question becomes, how can we use this information? What types of problems might we be asked? So one thing that we might be asked is to kind of solve problems relating atomic radii and the unit cell edge length. Okay, so here's a good example of that. It says the ferrite form of iron has a body-centered cubic unit cell with an edge length of 287 picometers. Picometers is a really common unit of measurement for when we're dealing with things at the size of a crystal's unit cell. And an important relationship is that 10 to the minus 10 centimeters is the same as 1 picometer. You might want to make a note of that and have that information handy. It's going to be important later on. So for a body-centered cubic unit cell, I'm just going to use that relationship from the table. The radius is equal to L root 3 on 4. So using the information that's given, I can solve for what the atomic radii is for this iron atom in this particular crystal. So L root 3 on 4 is just 287 times root 3 on 4, 124 picometers. All right, so that's kind of cool, right? Okay. Can we do anything else? Well, let's kind of do it again just to see an interesting point, right? The austenite form of iron doesn't have a body-centered cubic unit cell, has a face-centered cubic unit cell, has an edge length of that unit cell 361 picometers. So what is the atomic radii of iron in this particular crystalline form? So for a face-centered cubic unit cell, R is equal to L root 2 on 4. So again, we're just going to leave everything in picometers. So 361 times root 2 on 4, and we get 128 picometers. 128 picometers is slightly different from what we saw before, right? See, 124 picometers for the alternate form, and then in the austenite form, we get 128 picometers. So what you see is that the radii of an atom is a little bit fuzzy. It depends on how, what its bonding is. That's going to affect the radii a small amount, right? Okay, so just a couple of percent in this case. Something else that we can do is, as we know the number of atoms per unit cell type, if we're given the unit cell edge length, often referred to as one of the unit cell parameters, then you can actually calculate the density of a crystalline material. And this is very commonly done for metals. So ferrite, which was that first form of iron that we looked at, it has a body-centered cubic unit cell. The edge length is 287 picometers, and as I mentioned, 1 picometer is 10 to the minus 10 centimeters. And then we were asked to calculate the density of ferrite in grams per centimeter cube. So if I want to calculate the density of an object, I need two things, because density is equal to the mass over the volume, and we mentioned this before, the mass over the edge length of the cubic unit cell will help us out here. So the volume of one unit cell is just equal to the edge length cubed, so we can get that pretty quickly. The question is how are we going to get the mass of one unit cell? Well, it's not too bad because we know the number of atoms in a body-centered cubic unit cell. What we really need to know for this is, because it's body-centered cubic, there is 2 atoms. What is the mass of 2 atoms of iron, right? And if we can calculate that, then getting this density is going to be pretty simple. So first of all, we just have to figure out the mass of one unit cell. Because it's a body-centered unit cell, we know it's got 2 iron atoms in it. So a mole of iron atoms weighs 55.84 grams, but we don't want a mole of iron atoms, we just want 2 iron atoms. So in 1 mole of iron atoms, there is 6.022 by 10 to the 23 atoms of iron. Gets rid of that guy. And then we know that we've got 2 atoms of iron in our unit cell. So those 2 atoms of iron don't weigh very much. When you calculate the mass of a unit cell, it should be a really, really small number. If it's not, you probably forgot to divide by Avogadro's. Okay, you probably forgot to do this step here. So either not accounting for the number of atoms in your unit cell by looking at the unit cell type, or forgetting to divide by Avogadro's number is the most common error in these density calculations. Now we need the volume of our 1 unit cell, and we need that in centimeters cubed. That's not too hard because they actually gave it to us in centimeters, the edge length. So we just take the edge length and cube it, we get the volume, there it is. And again, should be a very small number. If your mass and your volume are not little numbers, then you have made a mistake. Now, to calculate the density, you just take the mass of your unit cell, divide it by the volume of your unit cell, and generally densities for metals are going to be about 1 to 50 grams per centimeter cube. If you're like significantly outside that, then you've made a mistake. Yep. Okay. So that's kind of calculating a density using some unit cell information. Yeah, so it's not too bad. Okay. So there is a worksheet that deals with calculating the densities and of metals and looking at the structures of metals that reviews a large amount of this content, and I would encourage you to have a look at that.